You ever look at a circuit diagram, one that's packed with inductors and capacitors, and just feel your brain start to hurt a little? Well, today we're going to talk about a mathematical superpower that can take one of the toughest parts of electronics and make it, well, a whole lot easier.
So you flip a switch in a circuit like this, and things get complicated, fast. The currents and voltages don't just change instantly, they have this whole dynamic response over time, because of the energy that was already stored in those components. And that's the big question for every engineering student, right? How on earth do you precisely describe what happens next?
Well, the textbook answer is, you have to write out and solve a bunch of pretty gnarly differential equations. And let's be real, that is a total headache. It's clunky, it's slow, and it is so easy to make a tiny mistake that messes up the whole thing. But what if there was a shortcut?
I want you to think back to a time before calculators. Multiplying two gigantic numbers was a nightmare. Then logarithms came along. And what was their magic? They turned that awful multiplication problem into a simple addition problem. Well, the Laplace transform does the exact same thing for us with circuits. It's our magic trick for turning messy, complicated calculus into nice, clean, simple algebra.
So how does this magic actually work? Well, the first step is we have to change our perspective a bit. We take our circuit, which we normally think about in the time domain, what's happening second by second, and we translate it. We move it into a whole new world, into a new language, the language of S.
Now, this is the formal definition, but don't let the math scare you. At its heart, all the Laplace transform does is take a function that depends on time, what we call f of t, and it morphs it into a new function that depends on this s variable, which we call f of s. That's it. We're just taking a little trip from the world of t into the world of s.
And here's where it gets really cool. This isn't just a simple translation, it's an upgrade. Because when we transform our components, any energy they had stored at the very beginning, like the initial current in an inductor or the voltage on a capacitor, it gets automatically packaged right into the new model. It just shows up as a simple little voltage or current source. This is a massive win, and it makes our lives so much easier.
And this is the payoff. This is why we go through that first step. By jumping into the S domain, we've basically left all the calculus behind. No more derivatives, no more integrals. We are now in the beautiful, simple land of algebra.
The process is fantastic because it's the same every single time. It's just 3 steps. 1. You transform the entire circuit into the S domain. 2. You use the basic circuit laws you already know and love, like Kirchhoff's laws, to solve for what you want. But it's all just algebra. And 3. You take that algebraic answer and transform it back to the real world, back to the time domain.
Let's actually see it in action. On the left, a standard RC circuit. We close that switch, and we get that classic exponential response. Now look at the right. That's the same circuit, but in the S domain. The capacitor C has become an impedance, 1 over SC, and its initial voltage is now just a simple voltage source in series. The whole problem just looks so much cleaner, doesn't it? Now that our circuit is in this new form, solving for that voltage V is a piece of cake. We just use basic tools like the voltage divider rule. And here is the absolute most important point. We get our answer for V of S without ever writing a single differential equation. It's just algebra.
Okay, so we have our answer, V of S. But wait a minute, what is V of S? It's an answer that only makes sense in this abstract S world. For it to be useful to us, we have to bring it back home. We've got to return to reality, back to the time domain.
And that return journey has a name, of course, the inverse Laplace transform. It's basically the undo button. It takes our nice, neat algebraic solution from the S domain and turns it back into the actual function of time that tells us what our circuit is really doing, second by second.
Now, you're probably thinking, oh great, here comes the hard calculus again. But nope, there's another shortcut here too. We use a neat algebraic trick called partial fraction expansion. It lets us bust up our complicated answer into a bunch of smaller, simpler pieces. And for each of those simple pieces, we can just look up its time domain equivalent in a table, and then we just add them all back together. Again, no complex calculus.
Now, just a quick reality check. This method is absolutely perfect for textbook problems. But in the real world, you're often working with noisy measurements. And when you try to do this inverse transform numerically, you have to be careful, because sometimes tiny little errors in your data can get magnified and give you a wacky result. It's just something to keep in the back of your mind. So far, everything we've done is to solve a circuit for one specific input. But the S domain unlocks something way more powerful. It gives us a way to describe the very soul of the circuit, its fundamental nature, completely independent of what signal you feed into it.
And this amazing concept is called the transfer function, or h of s. All it is the ratio of the circuit's output to its input, both in the S-domain. The best way to think of it is as the circuit's DNA. It's the unique genetic code that defines everything about how that circuit is going to behave.
The power this gives you it's just incredible. Once you know a circuit's H of S, you can predict its output for any input you can imagine. You just take the input, transform it, multiply by H of S, and you've got your output. It completely characterizes the entire system.
What the transfer function really reveals is the circuit's memory. The output at any given moment isn't just about what's happening to the input right now. It's actually a weighted average of all the inputs that have ever come before it. The circuit literally remembers its entire past, and that history shapes its response in the present.
So why do we go through all this abstract math? It's because understanding a circuit's fundamental DNA is what lets us predict and design for real-world situations. And sometimes, those situations are absolutely critical.
Take a practical power circuit like this one. In the real world, loads are constantly being connected and disconnected. By figuring out its transfer function, we can understand its natural response and predict exactly how it's going to react to these sudden changes before anything has a chance to go wrong.
Because if we don't do that analysis, this is what can happen. Look at this graph. This shows the moment a heavy load gets disconnected. The voltage was sitting there, nice and stable at 170 volts. And then, boom, it spikes instantly to 425 volts. That's almost triple the normal voltage. This is a real, dangerous surge, and it's exactly the kind of event that Laplace analysis helps us predict and engineer our systems to prevent.
Which leaves us with a final, pretty mind-bending thought. The transfer function is the circuit's DNA. It's the fundamental blueprint of how it works. So if you know that DNA, what does that really mean? It means you have the ability to predict how that circuit will respond to literally any signal you can imagine, any signal in the universe. And that is a truly powerful idea.